Welcome! Welcome to the Plasma Physics course of TPFL. In the past modules, we have shown how the Vlasov equation can be derived. We have pointed out that some analytical progress is possible. In some particular cases, we have focused our attention on two-stream instability. Now, unfortunately, it's very difficult to progress analytically in most of the cases, and therefore plasma physicists have to turn themselves towards the use of numerical method in order to solve Vlasov equation and approach the dynamics of a plasma. The goal of the present module is to give you a short introduction to numerical methods that are used for solving the Vlasov equation. The first thing that I will do is I will tell you why simulating plasma is so complicated. And it's basically because of the wide range of spatial and temporal scales that are involved by a plasma. Second thing that I will do is to introduce a numerical method, the PIC method, particle in cell, that is used to solve a Vlasov equation. Okay, let's draw a time arrow through which we will represent the timescales that are present in a fusion reactor. I will look at them in seconds. There will be phenomena on very short timescales, 10 to the minus 10, 10 to the minus 8 seconds, and phenomena that occurs on very much longer timescales. The fastest phenomena present is the electron cyclotron motion that occurs on a timescale that is smaller than 10 to the minus 10 seconds. The second phenomenon that is observed is the ion cyclotron motion that occurs on a timescale of the order of 10 to the minus 7 seconds. And then in all these devices to confine plasma for fusion purposes, there is turbulence present, and microturbulence occurs on a time scale of the order of 10 to the minus 5 seconds. There are global instabilities that occurs on a time scale of the order of 10 to the minus 4, 10 to the minus 3 seconds, and these are the fast global instabilities. There are so-called slow global instabilities on a fraction of a second. The energy confinement time in these kind of devices is of the order of the second. And then there are phenomena that occur on even longer time scale, for example, the equilibration with the gas equilibration with the vessel walls. A wide range of phenomena, therefore, that occurs on time scale that are separated by 10 to the 12 or even more orders of magnitudes, all non-linearly coupled and interacting. And similarly, we have also that I won't go into the details, but we have also that a wide range of spatial scales are involved. Representing all these phenomena at the same time is extremely challenging for computational purposes. And this is why plasma physics is at the forefront of the development and exploitation of numerical techniques. And despite the complexity of the phenomena that plasma physicists have to deal with, significant progress has been made in the field thanks to the use of numerical simulations and thanks to the computational power that is increasingly available. For example, here is the result of one of the state-of-art simulations that are done in plasma physics, a kinetic simulation of turbulence in the core of a tokamak device. This simulation has been run of one of the fastest computers in the world, has been done by using 10,000 processors, and in total more than 1 million CPU hours has been devoted to obtain the result we are looking at here. I believe that I have given you an idea of why simulating plasma dynamics is so challenging. Now, let me finally go to the point of our module, that is, what are the numerical methods that can be actually used to solve the Vlasov equation? Well, let me say that there are different techniques. On the one hand, we can discretize on a grid at a 6-dimensional phase space and advance the Vlasov equation in time. Well, this is possible, but is not typically the scheme that is used to approach numerically the Vlasov equation. The numerical method that is typically used is the so-called PIC, particle in cell method. And now I will tell you the ideas behind this method. I first start by recalling the Vlasov equation. Which states that the variation of the distribution function is due to the streaming velocity in configuration space and in velocity space. This equation can be interpreted, as we have seen in the previous lecture, by saying that along the trajectory of a particles, that is in phase space given by dr dt equal to v, and dv dt equal to q over m e plus v cross b. F is constant. In other words, that df dt is equal to 0. How can we represent this in phase space? We can project the 6-dimensional phase space here on the 2 dimensions of this screen. Here will be the coordinate, spatial coordinate. Here we will have the velocity coordinate. And if we consider a particle starting with a specific velocity and a specific spatial location at time t equal to 0, and we follow the trajectory of this particle as a function of time, well, the distribution function f will be constant as we move along this trajectory. The PIC method is based on this consideration. PIC means particle in cell method. The method is based on representing the distribution function at initial time t equal to t0 as the sum of a large number of functions that we will call f alpha, that depends on the spatial coordinate and the velocity coordinate, where this f alpha have the properties of having compact support. Therefore, they are equal to 0 everywhere except in a region of the phase space, and to be symmetric with respect to R alpha 0 and V alpha 0. These F alpha, as we will see the reason soon, are also called superparticles. Well, what does it mean? If we look at the projection of the phase space, we will see that these F alpha are everywhere, they have a compact support, therefore they are everywhere 0 except for a small domain, and they are symmetric, and therefore they are centered around the R alpha 0 position and V alpha 0. We introduced the integral I alpha of the particle of the F alpha of the superparticle function as the integral over the full phase space, so dr dv of F alpha. And then we will impose that at all times f is still given by the superposition of these superparticles. Which are centered at a position R alpha and V alpha that varies in time. In particular, if we require that these R alpha and V alpha satisfy the following equation, which resembles very much to the equation of motion that we have just written for particles, except for this E alpha and B alpha term that have to be defined, and we define according to an integral that takes that weights the electric field according to where the position of this superparticle is in phase space. And analogously for the magnetic field, imposing the initial conditions then we have that if we try to evaluate the convective derivative of d over dt of f alpha as R alpha and V alpha follow this equation, then we will have that this will be approximately equal to 0, which means that f defined as the sum over all superparticles is a solution of Vlasov. In other terms, how does the peak code particle in cell method work? Well, what one has to find are the R alpha and V alpha that satisfy the equation of motion that I have written, starting with the following initial condition, which means basically to follow a certain trajectory. And then once you have found R alpha and V alpha, you can evaluate the F alpha that are here, sum them up, and what you obtain is an approximation of the distribution function at all times. So how does the peak method in practice work? We will focus on one-dimensional system, and we will look at electrostatic limits. Now, if we know the charge present in a system, then by solving the Poisson equation, we can estimate electrostatic potential. And once we know the electrostatic potential, we can deduce the electric field as minus the derivative of phi with respect to x. Now, to solve the Poisson equation numerically, we have to discretize space. And we will introduce a grid where we will discretize x with x0, x1, x2, etc., xj minus 1, xj, xj plus 1, etc. And similarly for time, that will be discretized with t0, t1, t2, ti minus 1, ti plus 1, with grid spacing delta x that is constant and is therefore equal to xj plus 1 minus xj, and similarly for time. The charge density will be evaluated on the points of this grid. and will be denoted as rho J I, and this will be the charge density at location xj and time ti. And similarly we will do for the electric field and for the electrostatic potential. At this point on this grid we need to discretize the derivatives. And we will have that d phi dx at position j is approximately equal to the finite difference between the phi evaluated at point j plus 1 and phi at point j minus 1 divided by 2 delta x. And by combining similar expression from first order derivative, we will have that for the second order derivative at position j, a good approximation will be provided by phi j plus 1 minus 2 phi j plus phi j plus minus 1 divided by delta x squared. Therefore, coming back to our Poisson equation, we will have that phi at time I position j plus 1 minus 2 phi I j plus phi I j minus 1 divided by delta x squared, which is equal to minus rho ij divided by epsilon 0. And similarly for the electric field, this will be given by 2 delta x, the difference between the electrostatic potential at position j plus 1 and j minus 1. Once we have evaluated the electric field, we have to evaluate the electric field acting on a superparticle. For this, we will assume that the electric field is equal to Ej for x that are between xj plus 1 half and xj minus 1 half. What does xj plus 1 mean? That's the point in between xj and x plus j plus 1. And as we have just seen, the electric field acting on the superparticle alpha, which is defined as E alpha, double integral of E f alpha dx dv, can be readily evaluated if we assume that f alpha is equal to the product of delta Dirac function centered around x alpha and v alpha. This f alpha, which is the simplest that can be used in a peak method, has the properties that we have just listed. It has a compact support, in fact is equal to 0 except for a finite region of the phase space, and is symmetric. Is symmetric with respect to x alpha and v alpha. Well, with this definition, one obtains that E alpha is equal to Ej, being the distance between xj that is considered here and x alpha less than delta or equal to delta x over 2. Therefore, here we can have the electric field acting on a superparticles by knowing that the expression that we have already derived here, Eij, will give us E alpha. At this point, we have everything to solve Newton equations for each superparticles. That is dx alpha over dt equal to v alpha and dv alpha over dt equal to q alpha over m alpha E alpha. To do that, we discretize the time derivative as we have done for the special derivative, and we will have that the difference between x alpha at I plus 1 minus x alpha at I divided by delta t is equal to v alpha. We will consider it at 1 plus half, and with a similar law we will evaluate the advancement of the velocity. With this equation we can advance particle velocity and position. And by advancing particle velocity and position, we can assign the charge to the grid, to the spatial grid that we are considering. In order to evaluate the charge in each cell, this will allow us to solve Poisson equation. We will notice that rho j will be given by 1 over delta x. The charge contained inside each cell, and which will be given by the integral of the distribution function that we have approximated as the sum over all the superparticles, which have all a charge q alpha, and is integrated over the velocity, direction, and the grid in spatial direction from x j minus 1 half to j plus 1 half. This is in other terms equal to 1 over delta x sum over all particles that belongs to the j cell q alpha. And let's write it explicitly, summing. This alpha that belongs to j, we mean summing over particles, superparticles, such that their position is in between xj minus 1 half and xj plus 1 half, from which we can close our system by assigning rho j, as we have seen, sum over all particles that belong to the jth cell. So here is how the peak method in practice work. We start by giving an initial condition where all the particles position is known, from which we can evaluate the charge distribution. By solving Poisson equation we evaluate the electrostatic potential, and from this we have the electric field. From the electric field, evaluating from the grid, we estimate the electric field acting on a superparticle, and once we know the electric field acting on superparticle, we can solve the Newton equation for each of the superparticles that we are through which we are discretizing our distribution function. And here is the Newton equation that we can solve to advance at the next step the position of the particles. And once we go to the next step in position, we can evaluate the new distribution of charges, assign the charges to the grid, and go on by evaluating Poisson equation at the new time step, and so on. By advancing this system in time, we can actually look at the evolution of the distribution function, electric field, electrostatic potential in time and space. And the exercise of this series of lectures will be actually focused on a particle in cell peak simulation of a one-dimensional system in the electrostatic limit, where we will see two counter-streaming beams of electrons that interact between each other. So here we get to the summary slide, of the present lecture that has been devoted to the simulation in plasma physics. We have given a very short introduction of how models are approached numerically. Well, the first thing that I have done was to explain why is it so challenging to do numerical simulation of plasma. It's because of the wide range of spatial temporal scales at which phenomena occurs in plasma. Then I have briefly talked about the different simulation approach to focus then on the particle in cell method, the PIC method that is used in plasma physics to solve the Vlasov equation. Let me just point out that the PIC method is not only used in plasma physics, it's used in a variety of fields, starting from fluid mechanics to the study of dynamics of star in galaxy to the study of semiconductors. This is a fairly general method that, and we went into the details to explain how in practice this works in the simplest case of a one-dimensional plasma in the electrostatic limit.